cover most of kind of content-wise what we did, what you may have done in CS3130 or possibly some other or another math class. So I plan to go pretty quick. Okay, so outside this review and the linear algebra review, the other lectures should be at a slower pace, but for this one I'm going to go through it more quickly because there's a lot of stuff to cover. So, and hopefully most of you have seen it before, or if not, you might be taking the course at the same time. Okay, so we're going to talk about probability, and I'll start by saying, actually, why is probability important? Kind of there are three places roughly it's going to be needed. One, we're going to describe some algorithms in this class, which are going to be randomized algorithms. That means the algorithm will make random choices. And basically, in some cases, it's known there's no good way to solve a problem without using some random choices along the way. So to understand how to talk about those algorithms, we need to have a foundation in probability. Could also be that we're just thinking about how much data do we need to answer some question about the accuracy of some approach. And so the kind of quantifying this is it's going to have a process as you get more and more data, you're going to get more accurate, but it's not going to be with certainty. It's going to be a probabilistic guarantee. Right? So again, we'll need the language of probability, and then we'll do some very light kind of Bayesian analysis of data. Introduce this, and again, the language of probability. So this will be kind of a refresher, so you get the common language and so the notation. And so part of this lecture will be introducing this notation. Again, if I use a symbol or something which is unclear, just let me know, but I'll try and point it out as we go. All right, so the first key concept that we need is going to be a what's called a sample space, and we'll use the uppercase Greek letter so omega to denote this. So generally, and this is the space of possible outcomes. Okay, and so one outcome we'll use so lowercase omega is going to be an element of this set. So this is an element of this set. This will be an element. So you think of this as a set. We'll see it could be a discrete set or it could be a like continuous set. Okay, and then we're also going to have so this would be an outcome, and then an event A is going to be a subset of the sample space. Okay, this will be a subset of outcomes. Okay, so the kind of nice example of this is a six-sided so die, right? So this is an example, and the sample space here, if I roll the die, the sample space is going to be 1, 2, 3, 4, 5, and 6. Okay, and an outcome. So omega, and when I write it on the board, it looks kind of like a W, right? Is possible one is going to be 3. I could roll the die, and I'm going to get a 3, right? And so an event, it might be just an outcome. It might be I just roll a 3, but it could also be a set. So say 1, 3, and 5. These are all the these are all the odd numbers, right? Okay, so this would be an event. I rolled an odd number on the dice. That encodes it could be a 1, 3, or a 5, right? So when I say an odd number, I rolled a 3. That's this particular outcome. Okay. All right. So once we have a sample space and we understand outcomes, and so these events we can talk about probability, and in this discrete case, then I can say the probability, and I'll write this PR of the event A, and an outcome is a type of event, so this covers the probability of a particular outcome, okay, is going to be assuming that there's an equal probability of having each of these outcomes, is then I can count. I can say the size of the of this event, 1, 3, 5, over the size of the entire sample space. 1, 2, 3, 4, 5, 6. This is equal to size of A over the size of the entire sample space. So if I write these curly brackets with things in it, this means it's a set, right? So if you haven't seen this before, this is a notation of a set. These are the elements in the set. And then these bars here, this is is called the cardinality of the set, which is the number of elements in the set, or the size of the set. Sometimes that can be generalized to continuous sets as well, but might use a different notation. Okay, so if these are equally likely outcomes, right, I can calculate the probability as the fraction of times that I roll and I achieve one of the outcomes in the event versus all of the outcomes. Okay. Okay, so hopefully this is not such a new concept, or if you haven't seen it before, hopefully this kind of intuitively makes sense. The next main concept is a random variable. Okay, so this is going to be a function from the sample space to some to some other domain. Okay, so this is and usually onto a value. Okay, so it's going to be a function x, right? So I'll write this as x. It's a function from the range of the sample space. So I define it. I take as input the possible outcomes, or possibly the events, and it maps onto so some other domain, and generally it's going to map from this space onto like the real numbers, right? So it's going to map onto some value, and then these are things like we can add these up and so forth, right? That's the most common case, right? So as an example of this, so let's say so I'm going to have a fair coin, and the sample space is going to be the heads and tails, right? Flip a coin, it's heads or tails. Now I can say I'm going to get some points depending on whether I get heads or tails, right? So x of h is going to map to, say, 1 point, and x of t is going to map to 4 points. Right, so often, maybe in a calculus class, you usually use a lowercase f or lowercase g or h or something as a function. We'll typically use uppercase letters like x, y, and z as these random variables. That tends to be more common here, although these are functions, and that's the right way to think about it. Okay, and so then, yeah, so I can, then I can talk about this is, what's the number of points I roll. I flip a coin, and if I get a tails, I'm going to get 4 points, and maybe I win the game if I do this a bunch of times get lots of points. Okay, but that's just a simple example. Okay.
I have a question like that.
Yeah, great.
Does it have to map everything in the sample space? Like, could it only map H to 1 and not map T to anything?
You know, I mean, there might be cases where you don't define the outcome for, say, tails. I define the outcome for heads. I don't define it for tails. And that might still be useful. Generally, it's only useful if you have it defined for the whole sample space. Maybe there are parts of the sample space that occur with probability 0, and then you don't need to define those, and it'll be kind of still useful. But in general, random variable maps from the entire domain of the sample space. Yeah. I don't know if you still call it a random variable or not. If you don't do that, there might be some nuance in the definition that doesn't matter so much. So, okay, so good. So now we can talk about probability. Okay, so what do we mean by probability? And let's say of an event A. And we're going to write this as a probability of A. Okay, so a probability, you know, in this case, we kind of jumped ahead and defined this here, saying there was equal probability of each of these items, but, you know, it doesn't have to be equal probability of each of the numbers on the die. Okay, it could be an unequal probability. One, it might be a rigged die, and one occurs more likely than the other things. But you need to satisfy three properties. Okay, so it needs to be that the probability of any event needs to be between 0 and 1. Okay, it could be 0, it could be 1, right? It could be in a, like, rolling a 7 happens with 0 probability. It's not in this sample space. Or maybe there's a die that never lands on 3 because of some strange, it's round on the bottom and it tips over or something like that. Okay, but it has to be between 0 and 1. We must have that the probability of the entire sample space is exactly 1. Okay, so that means that everything that could happen has to be in the sample space. I can't have something outside the sample space that could happen, right? So if I, it also means that it can't be larger than 1. I can't have, that's just, I don't know, that's just what the definition is. So 1 is the sum of everything. Okay, and then there's this third condition that you need to kind of build. You can break down a outcome into these disjoint pieces. So let's say I have a disjoint union A1, A2 up to AK, and these are subsets of the sample space. And I have so that AI intersect AJ is equal to the empty set. So these can't overlap, and if I took the union of all of them, it's going to be the whole sample space. Then the probability of the union of these elements is going to be equal to the sum of the probability of these AI. Okay? So if I have a disjoint union covering the sample space, then I can break down it into these parts, and the union of them is going to be exactly the full sample space. It's a disjoint union. But then, because they're disjoint from each other, they don't overlap in the sample space, I can add up the probability of the individual terms, and that's going to equal the union of these elements. Okay? Actually, this is also true as long as they that they don't have to cover the whole sample space either. This is still true. Okay, so let me draw kind of a picture here. So I like to think of the sample space here as this square. Okay, and now an event A that I'm interested in might be this whole space here. Okay, so I might have this whole space here is this event. Right, it could be any weird shape in here. And then I can carve this up into these pieces. This is A1. Maybe make this in color here. This region is A2. This region is A3. And then let's use green again here. This region down here is A4. Okay, so what I know now is that AI intersection with AJ, or I and J equals between 1, 2, 3, and 4. This is equal to the empty set for I not equal to J. Okay, so these don't overlap in any way in this space and what they're covering. And also I could write the probability of each of these things. I can think of this as the area in some way, right? So I can think of the probability, right? So the probability of A4 is going to be essentially this area, right? So if the total area of this is a unit square, right, then the area inside here is the probability of A4. Like I'm throwing a dart at the board, right? If it falls in A4, then that's the probability. And so that means that if I sum up these probabilities, the probability of A1 plus the probability of A2 plus probability of A3 plus probability of A4, this is going to be equal to the probability of A, which is a union of these four things. Okay, so kind of pictorially, this is the way I think about it. So another example here would be with a if I have a die, 1, 2, 3, 4, 5, 6, and I say that A is the event that the outcome is less than or equal to 4. So I roll the die and the value is less than or equal to 4. And I'm going to have two events, the odd less than 4. So A1 is going to be 1, 3. A2 is going to be 2, 4. Right? So that these are disjoint from each other. The union is equal to all of A. Right? This is equal to 1, 2, 3, 4. And the probability of A1 plus the probability of A2, this is going to be 2 over 6, 2 over 6, and this is going to be equal to the probability of A, which is 4 over 6. Okay, so this is the law of total probability, and so you can define a probability of events over sample spaces, and they need to satisfy these properties. Okay, these are kind of just definitions. This is the only kind of tricky one to understand. You can think of it either pictorially or just this discrete way, and as long as they're a disjoint cover of your overall event, you can add them up. Okay, great. So let's. I guess I had a different example, but I think this covers it. Okay, so probability can be continuous as well. So I think in CS 3130 or like a probability class, usually they'll introduce a concept in the discrete setting, and then you'll see, look, everything holds in the continuous setting as well. These are examples where the sample space could be things like time, right? Time is continuous. There's some time between the start of class and end of class. I can break it down to seconds, but there are milliseconds, and I can keep breaking down. So something like an amount. Think of something like just like rainfall. If I'm measuring how much rain has fallen, it's not, the number of milliliters, but it's some continuous quantity, right? So I want to say, talk about the probability of like rainfall. It could also be something like a mass, like like an acreage of land, right? So how many acres? How many acres is the land? If we ever build a new building for computer science, how much acreage of land is this going to sit on? Right. So that's I don't be on the campus somewhere, but I don't know how much acreage it'll take up. That's a continuous quantity. So I can't measure that in like the size of a dice. Okay? And so, okay, here's an example with time. So let's say there's this Swiss train, okay, and it's going to depart at 1:37 p.m. Okay, and it's a Swiss train. The Swiss are always on time, so I know it's going to happen at 1:37 p.m. But I don't know what the seconds are, right? So that means it's actually in 1:37:00 up to 1:38:00, right? So I have an interval. It's closed on this side. This is a square bracket, and it's open on this side. Okay, so there's some seconds in between here. It's a continuous quantity. It's going to fall somewhere inside of here, but I don't know exactly where. I could say there's an event. So there's event A. Let's say the first 40 seconds. Right, so this would be 1:37:00 to 1:37:40. Okay, out of 60 seconds in this minute, right? So this is an event. It's a continuous event. I can ask, what is the probability? The probability of A, the probability of this event. Even though it's a continuous random variable, I could say that this is something like 0.8. So maybe the driver is going to be avoiding risk. So I'm probably going to try and leave in the early part of the minute in case something goes wrong. I have time to make sure I definitely stay in this inside the exact time before I'm supposed to leave.
Before
yeah.
1:37 is over,
You'll be fired if he leaves at 1:38 in 1 second, right? So try and leave in the first 40 seconds of this
so
minute.
the departure occurs 80% in the first 40 seconds.
In the first 40 seconds. And I can say this works out in the same way as before. Now, this is not necessarily a uniform probability. If it was uniform over this, it would have been, it would be about 0.666, right? About 2/3 of the time I would leave in the first 40 seconds, but maybe it's not uniform. Okay, and I can define the probability of an event without specifying this for every possible event here at this point. I haven't specified for all possible events. I've just said this event, the first 40 seconds, occurs with 80% probability. Which means that, let's say, B is going to be this other event, which the time is going to be, let's say, 1:37:40. 40 to 138.00, right? So, and then it would have to be that the probability of B, if this is really a probability function, this has to be 0.2. Okay? I know they both have to be in this range between 0 and 1, and they're satisfied that. Everything needs to add up to 1. Okay? I need to have everything add up to 1. And I've got a disjoint decomposition of the entire domain here into A and B. If I put these together, it's the entire domain here. This is the entire domain. And so I know that if the union of them is the entire domain, that must be 1. And if I add them up, they must equal the probability of the entire domain 1. This one is 0.8, and this one has to be 0.2 by subtraction.
So we're still following that long-term probability, even if it's continuous.
Even if it's continuous, it still follows the law of total probability. This is the definition of probability. Right? So if something satisfies this, then it's a probability. Okay, so we've defined sample spaces, random variables, events, probability, even with continuous sample spaces. We're off to a pretty good start. Are people still with me? I mean, we're going pretty quick, but okay, good. All right, let's move over here. Okay, so let's talk about so conditional probability. Okay, so far we've talked about just basically one event or decomposition of events, and they're all nice. Conditional probability deals with when you have two events that might interact in some way, right? So I have two events, A and B, and these are both subsets of the sample space. Okay?
Is there any overlap between A and B?
There might be.
Okay.
There might be. That's what conditional probability, that's what it is used to describe. Okay? Okay, and so the conditional probability is written as the probability of A given the given B. This is the probability of A given B. That means I'm going to assume B is true, and then I'm going to tell you what the probability of A is. So I'm going to assume the knowledge that B is true, and then I can tell you something about A. And so it turns out I can write this in terms of a definition for this in terms of set operations, which is probability of A union B. That means A and B have to be true, divided by the probability that B is true. Okay, so I can write this using algebra and the set operations. Okay, so this is a definition of the conditional probability. Okay, and so again, I've got a specific way I like to.
Your operator on conditional probability is wrong.
Yes. Thank you. Yeah, I wrote A union B, it should be A intersection B. So A and B are true. So thank you. Okay, so the way I like to think about this is that I've got my entire sample space here. And now I'm going to kind of draw a nice picture with A and B. If things are nice, and we'll define what it means to be nice, then I can think of A as being, let's write in color here. So A, I can think of as being some strip through here. All the events in here are A. And then there's some other strip in here, which is going to go in the other direction. These don't need to be the same size, right? So this is the strip B. Okay, and so this area in the middle here where these are overlapping, this is A intersection B. A and B are true. Inside of here, if in the place where these events overlap. Okay. Now it might not be as nice. It could be that my sample space looks like this, and like before, A is some weird region that looks like this, and then B is this other strange region here, and so then still I'm going to have this overlap. This is A intersect B. I can also define the union of the two of them. I don't think I need the union for B. So, but then, it could be not nice either. This will be nice, not nice. Turns out this will be independent. This will not be not independent.
What is the shapes of the spaces these the event spaces represent? Like, would it be the same problem as like A has the same area, but was like a nicer shape, or is it just representation?
Yeah, so these are just kind of conceptual representation to help you out. I haven't really given you the reason to think of these yet. I'll try and do that soon. I don't want to jump too far ahead, right? So okay. All right. So well, before we think about when it might be one of these two cases, just to think of what does this conditional probability mean? A given B, that's the probability of the union, the probability of the intersection divided by the probability of B. Well, in this picture, it looks kind of nice. I say, I know B is true, so basically I've got this new sample space here. I can think of this as my sample space B. Right, so now I know the only events which have happened are those which are like B, and then I'm just looking at this area, which is the intersection. The only part of A that's relevant is the part that intersects. Okay, and so then the total probability, instead of the fraction of the volume that was A, and I thought of this as maybe having a unit volume to start, I've now reduced the volume to B that I care about. And now it's just the fraction of volume inside of B. And here it looks like a rectangle again, and that's one of the reasons why this is nice. But the same thing holds true here as well. I also have this new restricted sample space, omega b, but it's no longer this nice kind of rectangle. But I'm basically looking at the probability of this event, that they're both true, normalized by the probability of b. That's the conditional probability. Okay, so you can think of it as just, when I condition on B, I'm shrinking the space of possible outcomes to those where B is true. So I'm restricting the sample space to be smaller, and you get this formula. Okay, good. Okay, so now, foreign concept is that two events A and B are independent if the probability of A given B is equal to the probability of A. Okay, so there are other equivalent ways of writing this. It's also true equivalently that the probability of B given A is equal to the probability of B, and the probability of A intersect B is equal to the probability of A times the probability of B. Okay, so if you look at this definition, okay, these three, you can derive any one of these others from the first one just by moving around this definition, right? So if I substitute this in here, then I can solve for this one, and by using both of those, I can derive this one. Okay, so the fact that I can say the probability of them both being true is the product of those probabilities is going to be very useful in many places later in class. Okay, it's going to be often, a lot of times when we model data, there's going to be some assumption that certain events, certain pieces of data have independence from each other. And this will be essential for making the kind of the rationale behind the analysis we use actually work. And it's going to be because of this formula here. Okay, so let's go back to these two examples. Okay, it's going to turn out that this one is going to be independent, and this one is going to be not independent. Okay, so let's look at why this is. Okay, because I drew these nicely as these rectangles where A is kind of an event describing on this side, it only controls the y value, and B only controls the x value. You know, it doesn't, what the x value does not control what the y value is one way of thinking about it, right? So think of this event space maybe as controlling two different things. It could be the time I wake up at night and the time so the time I wake up in the morning and the time I'm going to sleep at night. Now, it could be that these are dependent of each other, but they might be independent. This is the time, well, let's say I'm conditioned on this. So let's say the time I woke up in the morning, and this is the time I went to sleep at night. You know, if I'm always going to go to sleep at night between like 11:30 and like midnight, and it's say uniform inside this range, that may be unaffected of when I woke up between 7 and 8 in the morning. Okay, so I'm going to wake up at some point in the morning, but when I go to sleep, it's not going to depend on this. So if I tell you when I woke up, well, I'm still uniform there, even though that's the time I woke up. Now, it could be those are dependent, you know, but in this case, they're not. Okay, and so basically, it's when this is a strip in one dimension, this is a strip in the other, then restricting one dimension does not change the fraction of the y values that could be hit in the other dimension. And so that kind of makes them independent. The probability of, you know, of the times I went to sleep did not, was not affected by the time I woke up in the morning. Okay, and again, and you can flip the axes, and you can get, this is just flipping the axes. There's nothing special about either A or B. And this one is the product, right? So the area inside of here is the product of the x-coordinate, the fraction of x-coordinates which are allowable, and the fraction of y-coordinates are allowable. right? So let's say this was 50% and this was 30%, right? So if this strip was the probability of B, if this was 0.5 and this was 0.3, then the area in here should be 0.15, right? That's 0.5 times 0.3. Right? And if you actually calculate the area of this box, that's what it's going to be. It's going to be 0.15 in area. Okay, if they're not independent, that means the choice of A restricts B in some strange way. And it's possible, I mean, maybe I've drawn these so they actually are independent. It could be that the volume of A restricted to B is the same as the volume A restricted to the whole sample space. But that's not necessarily true if I don't have some nice structure. There's usually nice structure if they're independent, but to check, you really should do the calculation if you can. Okay? In these continuous settings, it's hard to do the calculation. Maybe I know something about these shapes and I can apply Green's rule or something weird like that, but in general, you're not going to get problems that look exactly like this. You'll be given some quantifiable way to do these calculations. Okay, good. So these are, where are we here? Okay, so these are two events are independent. Let's do another example with a probability table. All right. So a nice kind of convenient way of talking about probabilities that allows me to ask some nice questions about it on the homework, for instance, would be a probability table. And so an example would be with I'm going to have two random variables. Okay, so I'm going to have T is going to be a test for cancer, and this is going to either go to 1 or 0. 1 means the test indicate I have cancer, thinks it indicates I have cancer, and 0 says I don't have cancer, and C is actual cancer is 1, otherwise it's going to be 0. Okay, so you can then draw this in a table where you say okay, we'll say C equals 1, there's actual cancer, and C equals 0, I don't have cancer, but then I do a test, T equals 1, the test is positive, T equals 0, the test is negative here. Okay, and now this will be this, now there could be some like geometric space I think about this, but my only interaction with it is these kind of two random variables. So then I can write the probability inside of this table. 0, 5. Right, so this is saying the probability that I have cancer and the test is positive is 0.1. That's 10% of the time. Okay, of the people who are given the test, the probability they have cancer is going to be and the test is positive is 10%, but I might have cancer and the test is negative, another 5%. So the total amount probability I have cancer is actually 15%. Okay? It could also be that a cancer is negative, but the test is still positive. Okay? I don't have cancer, but the test says I do have cancer. This is not uncommon with the tests. They aren't actually perfect. Okay? Has to do with some unknown conditions that I don't know, we can talk about if we're in some sort of bioengineering class, right? But, okay, so there's 2% here, and so there's also the chance that I do not have cancer and the test predicts I don't have cancer. What is this probability? 0.83, right? I can use the law of total probability that these have to add up to 1. Right? These are all disjoint cases, and this is everything that could possibly happen. So they have to add up to 1. So that means 83% of the time people are tested, they don't have cancer, and the test says they don't have cancer. Okay. Okay, and so this is kind of useful to write it in this table form. You can ask a lot of questions. What's the probability that I don't have cancer? Yeah, this is 0.85, right? So this is equal to the probability of C equals 0 and T equals 1 plus the probability C equals 0 and T equals 0. Okay. What's the probability that I don't have cancer, but the test says I have cancer? Right? I would write that as the probability I don't have cancer and the test says I have cancer. And that's just this element in the table, right? 0.02. Okay. Now I can also say some conditional probability. The probability that I have cancer was 1, given that the test says I don't have cancer.
0.05.
Test says I don't have cancer, so it's not just the cell. It's not both. It's not and. It's the conditional probability. Okay. So now I need to write out the probability that I have cancer and the test says I don't have cancer, divided by the probability that the test says I don't have cancer. Okay, and let me erase this over here. Okay, so this is going to be the probability I have cancer, and the test says I don't. That's equals 0.05. Divided by the probability the test says I don't have cancer. I gave myself a hard one. That's the sum of these two things. That's going to be probability that C equals 1 and T equals 0 plus the probability that C equals 0 and the test equals 0. And this is equal to 0.05 and 0.05 plus 0.83. And so the answer is 0.05 divided by 0.88. Okay, so what is, that's roughly, was like 6-ish% of the time, right? So about 6% of the time, even if the test says I don't have cancer, I still do. So this would be be called a, in this case, a false negative, right? I predicted negative, but it was false. You know, I actually do have cancer. Okay, so these tests are not perfect. That's why sometimes they'll run more expensive or more invasive tests that are more accurate after a first test, which kind of might rule things out with some probability. Okay, if you know, if at some point you have kids, they'll run these tests earlier on in the pregnancy, and then they'll say, well, here are some probabilities of this happening, and if this test comes out positive, then we'll test again later on, or something like that. Okay. Okay, so is the test independent from having cancer?
It seems that it is.
No, it's not going to be independent.
But it's just a test.
It's a test. So that would have to be true. Okay, I haven't quite. I need to find.
But the test
Actually,
is influenced by whether or not you have.
Yeah. So let's come back to this. I realize I didn't give you the definition yet to answer this question. So I'll say two random variables. Let's say x and y are independent if for all events A in x and B in y, A and B are independent. This is if and only. Okay, so I defined the independence before for two events, but I asked you about random variables, the cancer and the test. Okay, so the probability of cancer given I went to have the test, and the probability that given that I took the test, what it returned. And that means that for any of the events, and in this case these are binary random variables, so the events are, the interesting events are going to be just, 0 or 1 and 0 or 1 or the entire sample space. Okay, so one way of checking this is I have this, I can look at these particular events. A can be C equals 1 and B can be T equals 0. Right? So in an example here, so I could say A equals to be C equals 1 and B equals T equals 0. Right? So the two events here have to do with these two things. Right? And so these are going to be independent if these two events are independent. And so one way of comparing this is they're independent if C equals 1 is true whether or not the test is 0. Okay, the probability of C equals 1 that I have cancer given the test. And I said that the probability that I have cancer given the test is 0 is 6%. But what's the probability that I have cancer overall? That's going to be the sum of these two columns. That's 0 that I have cancer. The sum of these two columns, that's going to be 15%. Okay? The sum of these two columns is 85%. Okay? So the total probability I have cancer is 15%, but the probability given the test says is 0, it goes down to 6%. Okay, so that means that they are not independent because this would have needed to be equal to each other. Okay, so in order to show they're not independent, I just need to find one pair of events which are not independent to each other. To show two random variables are independent, I need to show for all possible events that the events are independent. Okay? And it's trickier to show they are independent than to show they're not independent by finding an example like this. Okay, so is it good that the test and the cancer are not independent? Is that generally a good thing for a test or a bad thing?
We have a vote for bad over here.
It's turns out it's yeah.
It's a good thing your test should be more commonly finding cancer if patient actually has it.
Right. So why is that a good thing? Why
the test is accurate.
Right. It's telling me something. It's changed. Just saying I should have taken the test, I had 50% of probability. But if it comes back negative, I'm saying, oh, I'm down to 6%. Well, I should go celebrate. Or maybe now it's still 6%. It's not that great of a test, but it's reduced it almost to 1/3 of what it was before. It's given me information, right? This has provided information for me. Where if this was independent, if I come back at a result of 0, I'm still at 50%. I'm like, that didn't tell me anything. I knew that before I took the test. I was already at 15%. Okay, so when you learn something when a test is not independent, it's dependent on if you have cancer. Okay, you're more likely to test positive if you have cancer. If it was more likely, let's say my probability of having cancer increased if the test was negative. Is that still a useful test? Let's say it went up to 25%.
I mean, as long as they're still not independent, you're still gathering information about the relationship or about the probability of cancer, regardless of what you label it positive or negative.
Yeah, right. So it's still useful. I probably should have switched the variables associated with the test and said that it's positive if it increases my likelihood of cancer, right? So I can always, it just meant I labeled the test wrongly, but it's still a useful piece of information. I just have to be careful how I use it. So okay, good. So that was conditional probability. Question? Yeah.
Can you re-explain how that top chart is independent?
Yeah, right. So, okay, so I don't have random variables here. I just have events and B. Okay, and the way I'm going to measure probability here is by the area in this chart. Okay, and so let's say that this we can go through this in a little bit more detail. Let's say this is from 0 to 0.2. This is 0.7, and this is 1, right? And this goes from 0 to 0.5 to 0.8 up to 1. These are where the changes happen, right? And so you can verify that the area of the whole box is 1 by 1, so the area is 1. I can write down the area, the probability of the event B here, and so the probability of B is going to be the probability that the x value falls between 0.2 and 0.7. It doesn't matter what the y value is, right? Actually, I can say B is the set xy in this domain 0, 1 squared, such that the x value is between 0.2 and 0.7. Right? I can define this set. Okay, this is a set of x and y values, which describes here, and I can say the area of B. I can integrate this out, and I'll skip the simple calculus, whatever, is going to be 0.5. Okay, similarly, I can define the area of A. Okay, the area of A is going to be 0.3. And that's going to correspond with the probability in this mental diagram. Okay, so the probability and the area of A is 0.3. It's all the y values between 0.5 and 0.8. Doesn't matter what the x value is. And with B, it's just the x values. And here, there are 0.5 of those. Okay, so one way to check independence is to see if this equation holds. And so I want the probability that they both hold to be the product of these probabilities. This is 0.3, and this is 0.5. So this should be equal 0.15. Now I want to check the probability that the intersection is going to correspond with the area of 0.15. Right? So the event A intersection B is going to be the coordinates x or y in 0, 1 squared. This is given or or like such that I want to say that x is between 0.3 or 0.2 is less than or equal to x, less or equal to 0.7, and the y value satisfies 0.5 is less or equal to y is less or equal to 0.8. Okay, so this is the definition of the set A intersection B. That makes sense, right? It's restricted x coordinate here, y coordinate here. It's this region. And so now I can intersect this. It's a rectangle. Its length here, the length of this rectangle is going to be 0.5, and the height of it is 0.3. And I know the area of a rectangle is the height times its width. And so the area of here of A intersection B is going to be, again, 0.5 times 0.3, which is, as it was before, 0.15. And that corresponds with the probability.
I understand that part, but it does say if given B, what is the probability of A is equal to the probability of A? If that's true, that's independent, right?
Yeah.
So how is that true for that graph?
Oh, okay, great. So you can algebraically derive these, but let's just look at this case here, right? So the probability of A is 0.3. Now let's calculate the probability of A given B. Okay? So now I'm going to, and so that's being defined here. Now I know that the numerator here is 0.15. I calculated that down here. And the denominator here, probability B, is 0.5. Okay? And so, run out of room here, 0.15 divided by 0.5. This should be, is this 0.3? Yeah? Okay, multiply them both by, yeah. So this is 0.3, which is exactly what the probability of A was. The other way to think about it is I've normalized this, right? I've shrunk it by half, and I can, so I've shrunk the domain by half, so I've divided by 0.5. I've shrunk it by half, so this gets inflated by 2. Okay. So good. Really the most important thing in probably this lecture so far that we'll use kind of specifically the most later on in class is if events are independent, then you're going to get this property. I can write the probability they're both true as the product of the two probabilities. This is probably the single most important thing from this in this lecture, at least conceptually. Hopefully you've all seen this before, but this will turn out to be really important. And this notation and way of thinking too. Okay, so we are, as I mentioned at the start of class, I'm probably going to have to leave early next week on Monday, so I'm going to push just a little bit further ahead than I had on the schedule and talk a little bit more on density functions, and then we'll wrap up after that. Okay. So for most of you, have you all seen this before? More or less? Okay, good.
More or less.
More or less. I guess, well, I guess it could be exactly this same thing before, and then that would, it's a weird
Stuff from 31
turn of phrase.
Pretty simple.
Yeah. Okay, so density functions are meant to solve the problem with the example I just erased about the Swiss train. These are useful usually for continuous random variables, where remember there was time and I said it was exactly this minute, but I didn't know the seconds and the milliseconds and so forth. And I could say I could write down the probability of a particular event, which was a window in time, but I didn't really know it for any particular value. I didn't know how to write that down for all events or write that in some maybe concise way. So a density function gives you the machinery to try and do this, and we need to use calculus, right? This was just a nice, fun picture. You could use calculus to do it, but you could. That was all geometry actually. So with density functions, you really need to use your calculus here, and so basically, so for a random variable x, I'll define a density function f of x. Okay, and so this will again go from the sample space, and we'll map this to R plus. This is the real positive real values. Okay. So that means the outcome is always, well, maybe it's non-negative. So this is all the real scalars, okay? And we'll say greater than 0, or greater or equal than 0, let's say is x in R, such that x greater or equal than 0. Okay? It could be a million, right? But it can't be minus 0.01. Okay, so this is a, and so this is useful for a continuous sample space here. So you can define a density function for discrete sample spaces, but really it's useful for continuous sample spaces. And so and it's going to be useful for saying that the probability that a random variable is going to end up in some event A. Okay, so I'm basically saying the probability of an event A of occurring using my random variable here is going to be defined as an integral now. So all the possible outcomes in this event, I'm going to integrate over those values. Okay, so I can define the probability in a continuous space as an integral. Okay, and right, so let's think we have this, this time window, and this is 1:37. This is 1:38, and I knew before that, this is 40 seconds. I knew 80% of the probability was in here, and maybe there's some density function that looks like this. All right, so this would be f of x, which is going to be this density function. Maybe this goes down. Okay, and so if I integrate, right, the integral is the area under the curve. Let's say this is the event A. Then the probability is this integral, the area under the curve. Okay, now if this is a cumulative density function, then, if this is a density function, if this is a probability density function, sorry, let me say this precisely. Okay. if f is a probability density function, and we'll usually write this as a, just say it's a PDF, not the document type, but the probability density function, then if I integrate all the events over the entire sample space of f of x, w, d of x, and this has to equal 1. Right? This is each possible outcome. Each possible outcome is disjoint from all other possible outcomes, even in continuous kind of mathematical definitions. So I can apply the law of total probability, and this is a disjoint decomposition of the entire domain, and I know the probability of the entire domain is 1, so this integral has to be 1. Oh, dw, thank you. Okay. Okay, so that means that the integral of under the whole thing would have been 1. I know it has to be in this range. It's the Swiss train, right? But it's loaded up in the front here. 80% is in here. That's the integral here. Okay. And an important point, kind of an important conceptual point though, is that the probability that x is equal to a particular outcome is not equal to f of x w. Okay, this is the most unintuitive aspect about this. I can't say the probability of a particular event. So why is this? Why can't I? I mean, this intuitively is what we want to say. Why can't I say this?
Well, because it's continuous, right? So when you're thinking about it from a continuous perspective, I mean, no matter how many intervals you take around that point, you're going to have infinitely more intervals within that point. So you'll never have to reach that.
So yeah, that's right. I can write down the definition of the integral. Remember, it's this fraction, and I have this kind of this denominator that I guess that's integral. Yeah, but the probability of any particular exact time down to the millisecond, I don't know what's smaller than a millisecond, whatever, but it keeps getting lower and lower probability of that precise. It's a continuous event, right? It doesn't, the probability of any continuous event is 0 unless there's these Dirac functions which you can sometimes get around that.
If x is a discrete random variable, that will.
Yeah, if x was a discrete random variable, then this basically holds. Yeah, then this is basically the definition of the random variable. But for continuous random variables, you have to define it with calculus, right? And so I have to define a probability using this integral here. Okay, and this is kind of unintuitive to do it this way. And because of that, we usually will describe a cumulative so density function. Okay, and this is often called the CDF. Okay, and this is kind of a transformation of this probability density function, which is going to be much more intuitive to work with. Okay, and I'll also write this with an uppercase f of x. Okay, and let's write this for some here. Okay, and this is going to be equal to the integral. So now I'm going to remember this. This will make sense when this domain is equal to R, or is a subset. Is a subset of the real numbers. Okay, so now that means the outcomes are on the real line, and I can say from omega equals to negative infinity. Say t here. Okay, so from negative infinity up to t, right? This will be f of x. So d omega. So now I have these events. This basically maps to, I say, event a of t, which is going to be the events on the real line such that omega is less or equal to t. Right, so I can only have these events defined as subsets less than or equal to t. Right, so here essentially I have that. I could have extended a all the way back to negative infinity, and I measured up to probability 40. Okay, and the nice thing about the cumulative density function is it is a so probability. So that means that f of x of t is going to be so it's always going to be between 0 and 1. It's basically the probability. This is equal to the probability of this event at, or that x is in at, defined in this way. So the cumulative density function is the probability of the random variable going into this event. Okay, so it's going to be between 0 and 1 because it corresponds with this probability, and right. So I can now think of it has to be between 0 and 1 again, where this value could have been very large. There could be a very skinny region which has a very high value, but the overall integral is still 1. Okay, right, and because it's defined this way as an integral, I can also define, if I just have the CDF, sometimes I just have the definition of the CDF, I can define the PDF again in terms of this using differentiation. All right, so I can go back and forth between them using integration and differentiation. Okay, so this is the point. There's an example which we'll probably go through on Monday. The most common PDF we'll come across is going to be the Gaussian random variable, and it's this kind of smooth bump that has an integral of 1, and we'll go through this example and see its PDF and CDF, either at the start or the end of Monday. Okay, we can maybe review density functions a little bit then as well, because I know this one a little bit faster. Okay, I'll see you then. Question for you.